Hey folks, we've been looking at forces on individual objects and how those affect the motion of the object, but we know that forces really are interactions between pairs of objects. So what if we have two objects in our problem that we have to keep track of? How do we deal with forces there, and how do we figure out the motion of those two objects that are interacting as they're moving? So here we'll look at that, and we're going to be using Newton's third law in order to help us answer these questions. Now, there is another approach to answering some of these questions. You don't always have to use Newton's third law, and that's what we call a systems approach. And so we'll get into that a little bit later on, a little foreshadowing there. So let's just talk about this by going through an example problem. We have these two blocks, and we'll say that block A is being pulled across block B. It's being pulled over to the right with a 50 Newton force here, and is going to slide over to the right then. We also are going to have friction between blocks A and B, but no friction between block B and the table that it's on or whatever it's resting on. So that is a frictionless surface, but we do have friction between blocks A and blocks B. And the question we want to answer on this is acceleration for A and acceleration for B for those two blocks. What are those values going to be? We've got information about forces. We need to get to information about acceleration. So we hopefully understand here that we're going to be looking at Newton's second law that relates forces and acceleration. Anytime we do anything with Newton's second law, we'll start with a free body diagram for each object. And we have two objects that are moving around here, so that means two free body diagrams as well. So let's do the top block first. So object A. That top block is going to be pulled downward by a force of gravity. And remember, that's an interaction between A and the Earth. And I'm going to be careful to label it that way here. So that's the force of gravity from the Earth pulling on block A. And then it's also getting an upward force, a normal force, because it's in contact with block B. And unless it's falling through block B or accelerating up into the sky, those two forces must be equal in magnitude. So this is going to be a normal force. It's a contact force between two surfaces, and that's going to be block B pushing on block A. All right, block A also has this FP, this pulling force, and that's 50 newtons to the right. That's FP. And we're told here that block A is going to slide over to the right across block B. So that frictional force that we're told about, remember, it tries to oppose the sliding of two surfaces past one another. So in order to oppose that, it would try and push block A to the left, or pull block A to the left here. Try and stop block A from sliding past block B. So this one is going to have a 30 Newton frictional force. FF equals 30 newtons. Okay, and then B, much like A, will have gravity acting on it. B is a bigger block. It's a 15 kilogram block, so we'd expect a bigger gravitational force as well. And I'll try and represent that a little bit bigger here, but my scale probably will be a little off here. Oh well. So that's the force of gravity, and that is the Earth pulling on block B. Okay, let's see. Block B is also in contact with block A, and so block A got a force because of that. Block B has to get a force because of that too. That's Newton's third law. If they interact, they each experience that interaction. So block A got an upward force from block B. Block B must get a downward force from block A. And in both cases, those are normal forces. So this is a normal force from block A on block B. That'd be the same size as this normal force was from block B on block A. Block B is also in contact with the table, and so that's going to be an upward force, another normal force. This one's going to be the table on B. And then there's one more piece that we need to have here, and that's friction. There is friction between blocks A and B. They each experience that force. Block A got a force to the left, and so block B needs to get a force to the right here. So that is going to be a force of friction from block A on block B. And I didn't label that over here. This is the force of friction. Oops. This is the force of friction from B on A. B is pushing on block A or interacting with block A, and A is interacting with block B. Okay, so now we can start solving or setting up some equations for these things. In the y direction, I don't really care what's going on. It's neither block is going to accelerate that direction. We're going to look in the x direction. So for block A, acceleration in the x direction, which is going to be the same as net force in the x divided by the mass. We can calculate that as being, let's see, all the forces in the x direction. So that'd be a positive Fp, I'll say to the right is positive, so positive Fp, plus, and then we have a 30 Newton force to the left, that's a negative, so a negative Ff, divided by the mass. And so then we have numbers for all of those. We can plug those in. Acceleration in the x then is going to be positive 50 newtons plus a negative 30 newtons divided by 5 kilograms. And so that acceleration for block A is going to be 20 newtons over 5 kilograms, or 4 meters per second squared in the positive direction or to the right. Next, we'll go back to block B and analyze forces on block B. Block B is a little bit simpler here. We only have one force on block B in the x direction, so that's easy. Acceleration in the x is going to be the net force in the x divided by the mass. And in this case, acceleration in the x, the net force is just going to be, to the right, our frictional force divided by m. And that value for the frictional force was 30 newtons. This time it'll be 30 newtons to the right instead of 30 newtons to the left, or positive 30 newtons. And the block B has a different mass as well, so we have to pay attention to that. That one was 15 kilograms. So then acceleration in the x for block B, I'll label this one for block A. Acceleration for block B is going to be, let's see, 30 over 15, so 2 meters per second squared. And that is also to the right, or in the positive direction. So as a result of this one force, up here, this 50 Newton force, we actually get both blocks A and block B accelerating to the right, but as we see in our calculations down here, block A is going to accelerate more rapidly than block B does. So block A will actually slide over the surface of block B, and will always be traveling faster than block B is. So with these third law problems, we just need to think about third law pair forces. So we had two examples. Only one of them ended up mattering for the calculations we did here. But in this one, we had a normal force from block B pushing on block A, and likewise one from A on block B. And then we had a frictional force from A pushing on block B, and a frictional force from B pushing on block A. So watch for those third law pairs. Keep an eye out for any interaction between two objects. Make sure those forces are represented on the free body diagrams for both objects. And then it's just a Newton's second law problem, but, two of them. So keep practicing with these. And make sure you draw those free body diagrams every time. Those are a lifesaver.